Hi, my name is Jorge Meza, and I'm going to present my argumentative exam. So now we have the first problem, and here are the calculations. So let's start with the angular frequency, which is defined with the following formula. K is the spring constant, and m is the mass. Also, we have the following formula, which is the period. And also, it means that the period does not change even if the amplitude is modified. Uh, Regarding the total distance, when the mass is released from A, it travels a distance of 4a in a full cycle, growing from here to here and back. When the amplitude is doubled to 2a, it also doubles. The distance doubles, becoming 8a. The maximum speed is calculated as follows. The maximum speed also doubles, becoming this final result. Regarding the acceleration, doubling the amplitude to 2a also doubles the maximum acceleration, calculated with this formula, and the final result is this one. We have the following graph, where we can see two curves representing the motion of the mass when released from two positions, A and 2a. We have two different lines, one with blue ink and the second one with pencil. The one that represents the amplitude A is the one with pencil, and the other one with the amplitude 2a is with pen. We can see that both oscillates with the same period, confirming that the period depends only on the mass and the spring constant, not the amplitude. We can observe that the total distance traveled in one period is greater when the amplitude is doubled, and the system covers a large range between the maximum positions. This helps us understand how increasing the amplitude affects the displacement without changing the oscillation time. Now we have the following problem. First, we calculate the angular frequency using the following formula, and the result was 12.24. Then we calculate the amplitude using the following formula, with a result of 0.97, then the frequency with a result of 1.94, and the period with a result of 0.51. Now we have these two following questions. And regarding those questions, the maximum speed was when x equals to 0, and the maximum acceleration was with a result of plus and negative 0.98. The speed of oscillating mass is maximum when it passes through the equilibrium position, and the maximum acceleration occurs at this result because it is directly proportional to the displacement. And now we have here the differential equation that describes the phenomenon. Next, we have this question that I'm going to answer it with my MATLAB code, which is here. I already run the three different required, the one that is underdamped, the critical damped, and the overdamped. How do we know which one is which? Here is an example of the one that is underdamped. Here we can see that the system oscillates before returning to equilibrium, and it exhibits that the oscillatory behavior because the damping isn't strong enough to prevent oscillations. Then we have here the next example, which is critically damped system. The system returns as quickly as possible without oscillating. This level of damping removes oscillations but ensures the fastest return to equilibrium without overshooting. And now we have the last one, which is this one. Here, the system shows slowly returns to equilibrium without oscillating. And the explanation is that this level of damping, the system doesn't oscillate, and it takes longer to reach equilibrium because the damping is too strong. And then here we have the one that was required with a damping constant of 0.5. such as the amplitude and the oscillation at 10 seconds is exactly at 50%. The result was that the system was underdamped. And thanks, that was my argumentative exam.